The problem statement of house robber goes something like this. You're a professional robber trying to rob houses along a street, and those houses are given to you as a representation in the form of an array called nums. Each of the values in the array represent the amount of money in the house. So, for example, house one has $1 in it. The first house on the street has $1 in it. And then, like, the third house on the street has $3 in it. They don't explicitly say that these are dollars. This could be any currency, but let's just assume that all of these values are integer values and they represent dollars. Your ultimate goal is to try to maximize the amount of money that you can rob tonight. And obviously, if you were to do this in a regular problem, you just add up all the numbers and just rob every single house. But the caveat is that you can't rob houses that are directly next to each other. So if I robbed the first house here, then I can't rob the second house. Or if I rob the second house, then I can't rob the third house or the first house. So I can't rob houses that are directly next to each other. And this is assuming all the houses are in a linear pattern. So the house at the end is not next to the house in the beginning. You can recognize that this is a dynamic programming problem because typically dynamic programming problems will ask in the form of maximums, minimums, or the amount of something. So in this case, it's asking for the maximum amount of money that you can rob tonight. So it should trigger you to think that this might be a dynamic programming problem. For example, if we just take a slight detour and just go to some other common dynamic programming problems, like 0, 1 knapsack, for example, you want to get the maximum total value in the knapsack. For edit distance, you want the minimum number of operations required to convert word 1 into word 2. Minimum path sum, same thing, you want to minimize the sum of all the numbers along the path. Unique path is a bit different, so you want to count how many unique paths are there. Notice how this is slightly different from minimum path sum, because in minimum path sum, you want to minimize the sum of all the numbers along its path. But in unique paths, you just want to count how many possible paths are there. Notice even in the grid, in minimum path sum, there's integers in the grid. So you kind of like want to add up each of the integers. But in unique path, there are no integers. You're just counting up one unique way is just going all the way down from the top left to the bottom right. In climbing stairs, it asks for how many distinct ways can you get to the top. In coin chains, once again, I think it asks for the fewest number of coins that you need to make up a certain amount of money. And lastly, in distinct subsequences, it wants you to count the number of distinct ways that you can get subsequences of S that equal T. Notice how even though some of them are technically quote unquote hard and some of them are easy, they all have like a similar type of code structure, and I'll show you that in this video. So now here's the code for the solution to house robber. I'm going to go through this solution line by line and explain how it works, every line in here, and how it relates to the ideas that we've talked about before. And lastly, I'll show how to scale this sort of pattern, template, or structure, whatever you want to call it, to any dynamic programming problem, including the ones that we've briefly mentioned here. To start, if we look out the bottom here, I have the original function, which takes in a parameter called nums, which is just the array of houses. And all it does is just return rob helper, which is a helper function that takes in the original array and this number is 0. I'll explain this number 0 in a bit, but right now I want to focus on the examples, which are the same examples that are in the leak code problem. So 1, 2, 3, 1, and then this array right here, it's the same array, and I'm just printing out the solution just to make sure that it works. So I can run Python and the name of the file, and I'll get out my answer 4, 12, and then this is just an example I made up. So in this one, you want to rob the 7 and you want to rob the 9, which gives you a maximum amount of value of 16. Now onto the meat of the problem, which is this helper function right here. For any dynamic programming problem, the very first thing you want to do is notice how your brain instinctively solves the problem and then break that down step by step. For example, when your brain sees a problem like this, it automatically knows that you should be adding up, the 2, the 9, and the 1. Those are the only things you can add up, and you can only add up the 7 and the 3. And then you want to compare the sums of those two values. So your brain knows that you should add the numbers that are not directly next to each other, and it knows that there are multiple ways of getting a particular answer. Not necessarily the specific answer asked by this problem, which is the maximum amount of money you can rob, but you can get a certain amount of money that you can rob through, for example, in this one, the 7 and 3 yield a value of 10, but that's not necessarily the best answer, but your brain knows that it can be an answer. So the approach I always recommend to do in a problem like this is to visualize it out by drawing a recursive tree. I'm going to use the third example that I have here, which is 71191, because it's not as straightforward as just adding up every other number like the other two examples were. We can picture the array as a street of houses, and we want to start our journey at the very first house, so the house at index 0. Once we're at the first house, that's when we want to ask ourselves, should we rob this house or not? Since you don't necessarily know the right answer to that question at this point in time, since you've only visited the first house so far, we should just try both options and then figure out which choice was actually correct later on. So I'm going to keep track of a couple variables here. I'm first going to keep track of the index. So I'm going to write index, and currently we are at index 0, right? Then I'm going to keep track of how much money we have at a particular point in time. So we have $0 to begin with. And lastly, we want to keep track of whether we can rob the house or not. And I'm just going to note this with a Boolean true or false flag. And in the beginning, it's true because we can rob the house at the very first index. So once again, this is the index that we're at. This is the amount of money that we've robbed. So money robbed. And this is whether we can rob a particular house at a given index. So let's say I rob this house at index 7. I'll end up with $7, but I'll put a false flag here indicating that I can't rob the house at index 1. And then if I don't rob the house at index 0, I'll still have $0, but I can rob the house at index 1. And I'm actually going to write out the indices here real quick just so that you guys can see clearly what house I'm talking about at each point. Now moving on to index 2, so I equals 2 now. Since in this scenario we can't rob the house anymore, it'll just be the same amount of money, but the flag will change from false to true because at index 1 we couldn't rob this house, which means at index 2 we can rob that house. That's why the flag changed. But in this scenario here, there will be two different branches. One of them indicates that I can rob a house at 1. So if I rob the house at index 1, I'll have $1, but I can't rob the house at index 2, so I'll switch the flag to false. Or I could just not rob that house again, and I'll still have $0, but I can rob the third house. Now, if this all seems a little bit complicated, like obviously the answer is just 7 plus 9, you have to remember that we're not necessarily going straight for the answer. We're finding all possible answers and then choosing the best one. We're doing this because we want to write a solution that scales to all sorts of input values, and especially large ones. This problem is easy to do in your head when I have this particular array, but what happens when I maybe even double the input or triple it or quadruple it? Not so easy to do in your head anymore. But in a program, I can just run the same algorithm and it'll give me the correct answer of 64. Now, this algorithm uses the concept of dynamic programming, which is the combination of two ideas. The first of which being multiple choices. Now, multiple choices happen because at each particular index, we have more than one decision to make. In this particular example, we only have two decisions or two choices, whether to rob the house or to not rob the house. But in other problems, you can have as many choices as the problem dictates, but all that really means is that there will be more branches at each of the indices here. And the other concept is memoization, or in other words, caching. What this means is that you're just storing values that you've computed already in order to save time in the future by not having to compute those values again. I haven't even written out the memoization part of the problem yet, so we'll do that together in a little bit, but for right now, we're just focusing on the decision-making part of the problem, which is the part that involves recursion and dealing with multiple choices. Now let's quickly go through the rest of this recursion tree so we can move on to the actual code. Going on to index 3 now, we see that we have $7 and we can rob the house at index 2. So let's rob it and let's not rob it. If we rob it, we'll have $8 with a false flag. And if we don't rob it, we'll have the same $7 with a true flag. In this scenario, we can't do anything. We can't rob this house. So we'll have the same amount of money, but we can rob the house at index 3. And then in this scenario, there are two options again. The first of which being we rob the house at index 2. So we'll have $1 with a false flag. And if we don't rob the house, we'll have $0 with a true flag. Now going on to the house at index 4, which is the last house on the street. In this case, I can't rob it, so I'm just going to have 8 and true. Up next, in this case, if we rob the house, we'll have 9 plus 7, $16 with a false flag. And if we don't rob the house, we'll have $7 with a true flag. Here we can have 10 and false or 1 and true. Here we just have 1 and true. And then lastly, we have 9 and false, or 0 and true again. So now finally we've reached sort of the end of our iterations at I equals 5, which means that we're at the end of the array. We still need to process the elements at the last index of the array. So I equals 5 essentially becomes our base case, because it's the point at which we stop and actually return and do something with the results that we've gotten so far. So here we can rob the house and we can't rob the house. So we'll have 9 and false and 8 and true. Here we can't rob anything, so we'll just have 16 and true. Here, 2 cases, 8 false and 7 and true. Here we can't do anything and true. Here we can do 2 things, 2 and false, or 1 and true. Sorry, I'm running out of space here. But here you'll have a true with a false flag, or a 1 with a true flag again. Here you can't rob the house. You'll just be remaining with $9, but you can rob the house at index 5 if there was a house at index 5. And then lastly, the 2 scenarios here are that you rob the house at index 4, so you'll have 1 and false, or you'll just remain with $0, but you can rob the house at index 5. I'm actually going to write out the actual values here. So here we have $9 that we got from this branch. If we iterate along this branch and make these decisions at this point in time across these indexes, we'll have and end up with $9. Here we'll end up with $8. Notice how in these 2 scenarios, the $9 is more than the $8. So this is the path that we would want to take. And this is the amount of money that should be returned in this answer, because this question is asking for the maximum amount of money that we can rob. Up next here we have 16, then 8, 7, 10, 2, 1, 2, 1, 9, 1, and 0. And we can obviously see here that the answer is 16, but we only see that because we can visually compare all the numbers at once just by looking at them. But in your program, it can only actually compare 2 values at a time that are directly next to each other. So I think now is a great time to actually start diving into the code, because once you've drawn out this recursion tree and you've gotten the actual answer, writing the actual code becomes trivial at this point. So you're going to start off with a variable called money robbed, and that's just going to be equal to 0. This is your base case. So if the index, and notice how index here is 0, 1, 2, 3, 4, 5. The way I'm iterating from level to level is by adding index plus 1 or index plus 2, depending on if I robbed the house or if I didn't rob the house. So I don't have any for loop or any while loop that's incrementing this index variable. I just increment it using a parameter called index that I increment each time I call the helper function over and over again. So each time it goes down a layer in the recursive stack, the variable index gets incremented. And that's how you end up seeing 0, 1, 2, 3, 4, 5. And it stops at 5 because that's represented in the code by having a base case at the end to stop all of the recursions. So length of nums here is 5. Let me change this back to an array of length 5. So at this point, since we started off by using 0 here, index is going to be 0. So it's not greater than or equal to length of nums. So that's when we'll jump into the actual recursive part of the function. Here I've describe both the choices. So let's start with choice 1. Choice 1 equals nums at index. So nums at index is the actual value at each of these indices, which this right here represents the amount of money that you can rob. So choice 1 is you're robbing the house. So you're going to add up the amount of money that you can rob at this particular position plus everything else after that with index plus 2. The reason it's plus 2 and not plus 1 is because, remember, instead of using the true or false flag here, I'm just skipping an index. So this line directly maps to this function call right here, where you rob the house at index 0. So you got the $7, but you can't rob the house at index 1. So that essentially means you can't really do anything. So that's why I just skip the index itself. And that essentially means you can't do anything. Notice how all we did was flip the flag from true to false. So you can immediately skip over to the next index. And then choice 2 just means you didn't rob the particular house at this index. Notice how it's the same function call, except you're only skipping by 1 index, but you're not adding the amount of money in the particular house that you're at. So this line 65, would represent the 0 and true case right here. On the next iteration, it's something similar. So choice 1 now is that you're robbing the house at index 2, since it was 0 at first and now it's 2. Since we added 0 plus 2 equals 2. On the next iteration where I equals 2, in this case, choice 1 will be robbing the house and skipping the next index because you know you can't rob that index anyway. And then choice 2 will be not robbing the house, so you'll have the same amount of money, $7, but you can rob the next house. So that's why I only skipped by one index. And lastly, if I keep following this one more time, I'll end up being at I equals 4, where the amount of money at that current house is 1, where 8 plus 1 is 9, and I'll get my final answer there. Or I can just not rob that house and remain with my $8. Notice how in the left case, the index is actually I equals 6. But since our base case accounts for index greater than or equal to length of nums, not just equal to the length of nums, that edge case is taken care of. So then we have our final answers of choice 1 is 9 and choice 2 is 8, and that's stored in these variables here, choice 1 and choice 2. That's ultimately what the function is returning. We're returning the variable called money rob, which we're making the maximum of choice 1 and choice 2. So what the function is going to do is it's going to go down all the way to the end here, and it's going to get 9 as choice 1. And then it's going to go through all the way to the end and get 8 as choice 2. And then it's going to say money robbed, which is the variable that I created up here, is the max of choice 1 and choice 2. So money robbed, in this case, money robbed would just be $9. And that's what would be returned to the function. So now that we're actually done processing this particular branch of the tree, I'm actually going to go ahead and erase it and then just replace it with 9. Because ultimately, that's what we're returning through all of these branches of recursive calls. We're just returning a single integer of 9. So I replaced this entire branch with 9. We can go ahead and do the same for a couple of these branches, and you can see how returning money robbed actually gets compared. This entire branch gets replaced with a 16. Here you're comparing the 8 and the 7, and obviously the 8 is greater, so this entire branch gets replaced with the max of 8 and 7, which is just 8. Here the 10 just gets replaced with a 10. Here the 2 and the 1 get compared, and the 2 is bigger than the 1. Here again the 2 and the 1 get compared, so all of this just becomes 2. This branch just becomes 9, and the last branch is just comparing 1 and 0, so that'll just become 1. When you compare the 16 and 8, you just get 16. 10 and 2 results in 10. In these branches that are sort of singular, like this one, where there's no branching or options, I can just replace it with the end result of 2, like I've done previously in the recursion levels that were down below here. And lastly, 9 beats out the 1. Here, the 9 gets compared to the 16, and money robbed becomes a maximum of choice 1, which is 9, and choice 2, which is 16. So on line 69, I'm just going to return money robbed, which is just 16. I can simplify this to just 10, and the 9 beats out the 2. Here, I'll simplify this to just 16, and the 10 beats out the 9. In our very last comparison, the 16 ultimately beats out the 10, and that's actually what's returned in money rob, and then ultimately what gets returned in the actual rob function. Remember, the rob function is just calling this helper function with the original array that's given and an index that starts at 0. So all it's doing is sort of starting off this entire process, and then at the end, when you're actually returning money rob, you just return the answer to that helper function, or you're returning the result of that helper function, and that'll actually give you the answer of 16, which ends up being the maximum amount of money that we can rob in the street of houses based on the constraints that we have been given. And that is the actual answer to this problem. This video is just way too long for my personal taste, so in the next video we'll talk about how to implement memoization in this problem, and then we can talk about the time and space complexities of a problem like this, and how this code structure here can be used for other dynamic programming problems.